Welcome back, everyone. Before we begin the afternoon sessions, just a friendly reminder to everyone to please complete the session feedback cards on your seats at the end of each session and hand them to a volunteer. Ben Smith is a senior software architect, Adobe community leader, and author. Today he's here to show us how to harness the power of OOP and write invaluable code. Please welcome Ben Smith.
Hey everybody, good afternoon. I'm Ben Smith. This is Harnessing the Power of Object-Oriented Programming, where we're going to learn to take advantage of the object-oriented languages that which we use. Today's technologies are built on top of object-oriented languages, and so it would behoove us to obviously understand how to take advantage of it so that we can best write invaluable code. Humans are very capable of recognizing objects under many variations and conditions. We use objects as tools. We use objects as symbols, and lastly, we use objects to simplify the world around us. Object-oriented programming is a paradigm that seeks to leverage our innate abilities to work with objects. This allows us to best organize, as well as mentally connect with the code that we write and work with. Now for this, in addition to other reasons, object-oriented programming is commonly touted as a flexible technology. But many people understand the object side, not too many understand the flexible side. The reality is that object-oriented programming is as simple as it is complex. Early adopters of the language can make objects within the hour. Yet just as easily as one can make an object, a developer could fall victim to writing rigid code. Now consider the class on the right, the person's class. It appears to be a flexible object, and it is. An instance can represent a variety of people as demonstrated on the left. We have Ben and we have Tina. And we could continue to create additional instances or representations. All we'd have to do is instantiate another person's class to which we will supply the appropriate details. Yet the context that must apply these details can easily bear the burden of such flexibility. Consider that of our manager class. Now I realize that the behaviors are truncated. I do this for simplicity. But if the code within these methods was ever to be considered flexible, if our manager, before it instantiated 3 persons, was ever to be considered flexible, it's now entirely rigid. And this is because an instance of our manager class will only and always manage 3 persons: Ben, Chris, and Tina. Now, just because we make use of an object-oriented technology does not guarantee that we're going to be writing flexible objects. The developer can write bad code just as easily, if not more easily, than one can write good code. The most powerful aspect of an object-oriented technology is the dynamic capabilities of the runtime environment. References are rarely bound to particular objects or behaviors, and therefore an application at runtime can constantly be evolving. Now in contrast, the most limiting aspect of an object-oriented technology is that of the author time environment. Unfortunately, this is where a developer is going to interface and write their code. And all code defined is fixed. And this creates a very unforgiving environment for a developer. What this truly means is that we're constantly on the cusp of injecting rigidity into our applications with every single keystroke. Therefore, an object, a structure in our application must be properly and thoroughly designed. Otherwise, it may fall victim to any of the following causes of redesign. Now, the most common cause of redesign is due to application requirements. If it wasn't for application requirements, application development would be a breeze. Unfortunately, we'd all be out of jobs. So it's important for all inexperienced developers to understand the techniques used to align both the author time environment with that of the runtime environment for flexibility, as they're the most susceptible to writing rigid structure. Unfortunately, this becomes a catch-22 because the techniques used to do so are often complex and only understood by experienced object-oriented programmers. Now the reason why is because unless you're a developer who's currently attending an institution where design solutions are part of your education, then unfortunately you're on your own. It'll be up to you to seek out design solutions, to interpret them, ingest them, digest them, and lastly implement them all on your own, and this is not at all an easy feat. Object-oriented programming makes heavy use of abstractions, layering, and lastly a technique known as indirection. Now indirection is when an object does not explicitly supply a behavior, yet through the reference of another object, that behavior is able to be fulfilled, and that's because that referenced object does indeed possess that behavior. Now, this is no different than if you can think back to maybe when you were 13 years old, and you made plans to meet up with a bunch of your friends after school at a destination such as the mall. Now, you didn't let the fact that you didn't have any transportation to get there stop you from making these plans, and that's because you knew that your parents had a vehicle and they possessed the ability to drive that vehicle, and sure enough, through them, you could be driven to your destination indirectly. But the real reason why object-oriented design is difficult is because the solutions that they make use of are the result of many accumulated understandings. And therefore, in order to take advantage of those solutions, you have to be able to differentiate between good code and bad code so that you have a context to understand what makes these solutions valid. Otherwise, you don't know what you're implementing. You're just following instructions, good or bad. Now, to provide this context, it helps for all developers to understand the SOLID design guidelines. Now, SOLID is a mnemonic acronym that stands for the following 5 principles: the single responsibility principle, the open-close principle, the Liskov substitution principle, the interface segregation principle, and lastly, the dependence inversion principle. Now, we'll begin with the single responsibility principle. The ideal scenario for all developers would be for code to never to become subject to change. Unfortunately, change is a constant, and it's just a matter of what particular aspects of our code will become affected. Our inability to predict where change will occur is reasons why, as a developer, we must ensure that when it does, it affects the least possible area. So consider the following real-world example. Your accountant is also your financial advisor, and on top of that, they're both your father. That's why I'm going to them, right? Save yourself some money. Anyhow, 35 days before taxes are due, you get a phone call. It's from your father, and he says, "Son, or daughter, your mother and I are moving to a tropical climate to retire, and this is happening toot sweet." Well, now you're just screwed. All right? It's 35 days before taxes are due, and not only is your accountant moving, your financial advisors are moving, and your parental units are moving as well. You might still be able to say that, hey, I can still take my father's financial advice over the phone, and that's true, I give you that. But you still have only 35 days left before taxes are due to decide whether you're going to try and file your own tax preparation or find another accountant that you can trust and pronto. The fact is that you allowed your father to play 2 additional roles in your life. And when change occurred, the impact became more significant. The single responsibility principle states that an object should possess only one responsibility, and therefore it possesses only one reason to change. Now, an object's possession of a singular responsibility is not the same as an object's possession of a singular method, so don't confuse the two. In fact, it could take a few methods to fulfill a single responsibility. A responsibility merely refers to the role that an object plays within your application. Now, here is our dad accountants class. Now, the top half of the behaviors respond to our father, and the lower portion of the behaviors are particular to our accountant. Now, in that story, change occurred due to a move. And that might seem a little unrealistic for our application to exhibit that type of behavior, but there are plenty of reasons for this object right here to require change. Consider the aspect or the responsibility of the accountant. Being an accountant is a highly specialized occupation, and they have to remain current with all of the federal regulations and state regulations so that they can best assist their clientele. Now, what this means is that every year, or when a law changes, this object is going to have to be modified to reflect the new abilities of that law so that he can best direct his clients. Now, every time we open this up, the behaviors of our dad, which were working just fine, will become victim to any bugs or errors that we inject into this because we have to modify the aspect of our accountant. So instead of allowing that to happen, because we know that these are 2 completely separate responsibilities, we separate them into the appropriate objects that they belong to. Now, when change occurs within our accountant, it's isolated from that of our father. Now, the single responsibility principle in no way prevents change from occurring, as change is a constant. It just minimizes the risk that could occur when change does manifest. Now, the additional benefits are that the behaviors become more concise towards a specific goal. And in turn, the goal that an object facilitates becomes more easily identifiable. Now, being able to identify the behavior of an object is going to be very important for the role of the developer. because we're using objects. We need that intransigent way to read a symbol so we can best understand what's going on in an application. We move on to the open-close principle. Code should remain open to extension, yet closed to modification. Now, extension emphasizes this notion of plug-and-play capabilities. Code should be programmed with this anticipation that objects may be required to work with our application in the future. And the dependencies, then, that are expected to make use of these new inclusions should be able to do so without the need for additional modification. Now consider that of our musician. I don't know if I'm too far from this. Now our musician object at runtime is able to be supplied two musical objects. And upon receiving one of them as a piano, it will determine the interface, which in this case of a piano is tickle, because one tickles the keys. And if it is that he's applied a guitar object, well then at runtime, he'll understand what this object is and the interface to which it must use, which is strum, because one would strum a guitar. Now unfortunately, if in the future we decide that we want our musician to be able to make use of a violin or a harp or a viola, and we instantiate those objects and we supply them at runtime expecting that they'll work, the application will fail. And that's because our musician at runtime remains unaware of the interfaces that these new objects will possess. Everything that our object does at runtime is a direct reflection of what we've put in within author time. Now for him to be able to make use of those new objects, we would have to modify the behaviors that you can see right here within his play behavior. Code such as our musician is said to be dependent on implementations and therefore must be refactored in such a way that provides extension through plug-and-play means. Now extension is ensured through abstractions. And an abstraction represents the behavior or the behaviors that can be viewed as characteristics possessed by possible objects. But they possess zero implementations. This is similar to a shape, a car, or a house. We're not specifying a particular shape or car or house. We're regarding them in mere sense of the words in general terms. They remain purely conceptual, and building up from ideals or principles are far less likely to change, and therefore they become the solid foundations to which we want to build our applications up from and around. Now in an object-oriented language, to devise an abstraction is similar to building an object. It possesses a responsibility, so it possesses behaviors, and it possesses a name as well. But it does not possess an implementation. Now that's going to be left up to the subclasses of that abstraction to devise. It's their responsibility to provide the behaviors or the operations to how those responsibilities defined by the abstraction will be facilitated. And they will do so in a manner that is unique to the object that it represents. The thing about separating an interface from an implementation is that by doing so, we ensure that our abstraction has zero reason to change. Now I just got through saying how they're going to be our foundations to build up from our objects. And that's a great thing because we don't want to build up an application that's going to have cracks or fall apart suddenly. Now additionally, because it's going to be the role of the subclass to supply the behaviors to the interface of the abstraction defined, we know that it must somehow possess an understanding of what that responsibility is defined by that abstraction. And through the use of inheritance in an object-oriented language, it actually inherits or adopts that interface. And this is great because now all of our subclasses of an abstraction, now they possess standardization or uniformity. And this is great news for dependencies such as our musician, who, if you remember, at runtime is unable to make use of the new inclusions of musical objects because he is unaware of their interface at author time. So if we can devise an abstraction that will represent the classification of all these musical objects, and say we call that instrument. An instrument possesses a behavior that will be uniquely inherited to all of these subclasses and provides a means for a musician to tap into their behavior, and let's call that play. Good. Then all of our subclasses will be able to inherit that play interface to which they will provide the appropriate implementation that is unique to how they will fulfill that behavior. You can see that we have our piano and our guitar, they're becoming subclasses, and they inherit that play interface. Now, all we have to do is refactor our abstraction around our musician so that he can make use of the instrument abstraction. And now you can immediately see that we no longer need to meet any conditions. We no longer need to try and figure out or determine which interface for the object we must use. And that's because we can safely assume that any object he is being supplied, as long as it is a subclass of our instrument, it will possess the play interface to which he will be able to make use of. So now when we pass in the piano or the guitar, he can play them through one line of code. And if in the future we create our violin or our harp or our viola, as long as they remain subclasses of an instrument, he too will be able to make use of them. Therefore, we have created extension without the need for additional modification. We move on to the list-off substitution principle. References surrounding base types must be able to make use of subclasses of said base type without realizing it, or without being aware of it. Now, the significance of such a principle is necessary in order to fulfill the dynamic capabilities of the runtime environment. The substitution of objects at runtime, which is commonly referred to as polymorphism, can only be made possible if the objects being passed remain indistinguishable from the referenced types. Now, subclasses are assumed to be capable, and assumed is the key word, assumed to be capable of fulfilling such a request of a client because as a subclass, it inherits the interface defined by its parent. Now, because it inherits that interface and supplies the responsibilities, we could exchange our subclass anywhere we make references to its parent's type. So, because of that, we often say that inheritance regards is-a relationships. Whoops. So what is it is-a relationship? Well, it just merely relates to the idea that a subclass can fill in for its parent's class because it inherits its behaviors. So here we have a checking account is a bank account, and a savings account is a bank account. These are two pretty valid statements. I don't think anyone would disagree. And we're saying that both of them stem from a bank account. So what this really means is that a checking account and a savings account should be able to be supplied anywhere the bank account reference is being used. So let's try this out. We begin with our obvious abstraction, our bank account. Now when we instantiate a bank account, we will supply it with a currency value, and this number will represent how much our valued account is worth. The bank account possesses a close behavior, and by invoking this method, the value of the account's worth will be returned back to the client. Now the client of this application is our bank. And while the bank possesses clearly many more methods than we're displaying here, we're only focused on one particular aspect, and that's going to be to close an account. All right, close account accepts a bank account type, so that should be our savings account or our checking account. Any one of our subclasses, it should be able to accept a bank account type. And upon receiving that bank account, it will make use of the close method defined by the bank account's abstraction. And by calling that method, the value or the sum of the account will be withdrawn, and therefore our account is now empty, so we can dispose of that. There's no longer a need to hold on to it. And then we'll return the sum of the value back to the owner of the account. So here's an example of our checking account. Now we instantiate our checking account for $100, to which we then immediately proceed to closing out the account. Now the account becomes closed, the value is withdrawn, we no longer need to hold on to that account because it's empty, so we throw it away, and we return the value of $100 back to the owner. Just what we expected. All right, so now we're going to do the same thing with a savings account. Now our savings account is instantiated, it's applied with the same value as our checking account, $100, and we proceed to close this account, and upon passing in the account makes use of the close method, the value is withdrawn. Then we no longer need to hold on to that record, so we supply it, we remove it from the bank's records, and then we return the value for $0. Well, that's not what we expected. So what went wrong here? Well, what went wrong was that the behaviors of our savings account did not adequately reflect the expectations of our client. Our client assumed that calling that close method was going to allow us to return all the value that it retained back to the owner, and therefore we no longer had to hold on to it because it should have been empty. And it's not that our savings account did not possess the appropriate behavior because as a subclass, we know it inherits that behavior. But you can see here that upon instantiation, our savings account sets a maturity date. And unless that maturity date has been exceeded, calling the close method does not withdraw the value. The implementation of this behavior then requires that the client, our bank, or at least the developer who created that client, make additional assumptions about how to treat this closed behavior. And therefore, the closed behavior defined by our abstraction no longer provided a standardization. When we viewed the is-a relationship, originally we viewed it in isolation, and it seems valid. The second time around, we viewed that relationship in according to how we needed our application to work. And it didn't pass what our test was. And the reason is because a savings account is a highly specialized type of account. So it can't be used anywhere that we have just our bank account reference. Possession of a similar interface is not enough to satisfy the Liskov substitution principle. Now, if we were to try and determine that that savings account should have been handled differently, we would have violated our previous principle, the open-close principle. We wouldn't have been open to extension, we would have been closed to extension, and only open to modification. Is-a relationships must pertain to the output that a client depends on. We move on to the interface segregation principle. Objects possess not only behaviors, but data as well. And the encapsulation of that behavior will localize the behaviors with the data that they require. And that's why we create objects. And now through the interface of the object, external factors will be able to message our behaviors or the data to which the object pertains. Then, upon messaging or being requested, the data is able to be manipulated or mutated, and through the association, the behaviors as well. By minimizing the interface or concealing the interface from the general public of our application, we can minimize the risk of data becoming manipulated improperly. This also enables the object itself to become the safeguard or the gatekeeper to the information to which it pertains or possesses. This is often known as data hiding or information hiding. Now, object-oriented languages provide a means by which you can conceal an interface. Some languages, such as Java on the left, they make use of access modifiers. Some languages on the right, like JavaScript, it requires a developer use scope manipulation. Now, unfortunately, we will never be able to completely conceal the behaviors of an object from the general public of the application. And unfortunately, again, because we can't do this, we can invite possibly erroneous behaviors into our application. The interface segregation principle states that the interface of an object should remain cohesive and relevant to the intentions of the dependency. Now, as I said, we can invite possible erroneous behaviors into our application if we avoid this principle. So what is a possibly erroneous behavior? Well, I have an example to demonstrate. Now, we're going to be looking at an example that focuses around the fast food industry. Well, particularly, we're going to be looking at three aspects of that industry: a worker, a work schedule, and a manager. Now, on the left, we start with our worker. Now, our worker possesses two behaviors. One is to work, that's why they're hired, and the other is to be able to receive their schedule so they can come in and work. Now, the weekly work schedule, as the name suggests, holds the hours for the workers for the week. And it possesses two behaviors. One is set hours, and the other is to get hours. Now, set hours will be used exclusively by our manager, and get hours will be used presumably by our workers. That's frustrating. Here are workers. We're already well acquainted with them, Ben, Chris, and Tina. They're going to be fulfilling the roles of our worker, so that means they're going to be supplying the implementations, the responsibilities that are defined by it. And here's our manager. Our manager possesses two behaviors. One is to make the schedule, and the other is to assign the workers their schedule. Now, when a manager makes a schedule, he instantiates a weekly work schedule, and he uses the set hours behavior of that schedule to be able to supply the hours for the workers for the week. You can see that Ben and Chris will be working together on Friday for 8 hours, the same shift. Now, when he is done creating his schedule, he will supply all the workers to which he manages, that's Ben, Chris, and Tina, the schedule that they require. Unfortunately, come Friday, Chris is not a happy camper. The manager apparently put him on the schedule for Friday by himself. Now wait a second, that can't be, because we just got through saying that Ben and Chris were supposed to be on the same schedule. So what just happened? Well, unfortunately, Ben made a mistake and mistakenly said his hours for Friday rather than get his hours for Friday. It's a very simple mistake. You can understand it's only off by one letter. This is a possibly erroneous behavior. Now this is worse than just a regular type of bug. You see, objects are passed by reference, not by value. So this means that this one change has actually made a change in the object that is held by Chris, that is held by Tina, and that is held by the manager itself. So Ben is not on anyone's schedule. So that creates a problem, especially for a developer if this was a real application. And that's because, well, we know that we're immediately going to jump into checking out our manager code because he's the one who is supposed to make use of the set hours behavior. But while we're around taking a look for anything that looks suspicious as to why this error occurred within our manager class, we're not going to find anything. And that's because nothing went wrong with the manager. Now what that means for us is that we're going to have to hunt throughout our whole entire application, searching for a bug, a very simple bug, which happened mainly because someone was receiving an interface that they shouldn't have even made use of. We need to nip that in the bud, because that really creates more additional issues for a developer, additional complications, and that itself is inflexibility. We're going to solve it with an adapter solution. All right? We're going to create another object. In this case, we're going to use a viewable only schedule, which will act as a wrapper to conceal the set hours interface of our weekly work schedule. And as you can see that our viewable only schedule, and as the name suggests, it only has the ability to get the hours. And it's going to actually, when it's instantiated, it's going to require that you supply the weekly work schedule instance within, and then once it's set, there's no access to it. No one could set the hours, no one could acquire that object. The only thing that we need to do is we need to update our worker to now receive from what was once the weekly work schedule to now the viewable only schedule. So that way they can only make use of the get hours. And when they use the get hours method of our viewable only schedule, you can see how the request will be forwarded to the weekly work schedule that it contains within. Now that behavior was working just fine for Chris and Tina, so we're just going to continue to make use of that behavior. And when that method is called within, it will compile the worker's work hours for the caller, and it will return it all the way back up until it reaches the originator of the message, which is the worker. All right, so now when our manager creates the schedule, he continues to do so as he always did. He instantiates a new weekly work schedule. He supplies it with the hours. You can see Ben and Chris are back on the same schedule for 8 hours come Friday. But now, right before he passes it into all of the workers to which he manages, he creates a new instance, a new object instance, our viewable only schedule, to which he will supply the weekly work schedule within. Now, no one has access to the set hours. And when he supplies this now to Ben, Chris, and Tina, they can only make use of the get hours interface, because that's all they have. So unfortunately, Ben, we'll see you behind that counter come Friday, bring your apron. We move on to the dependence inversion principle. All right, suppose if class A possesses a reference to class B, class A is said to possess dependencies. Now, depending on the type of level of dependencies, the reusability of class A may become limited. Now, suppose class A represents a button, and class A represents a specific type of lamp, a halogen lamp. Well, then we can say with certainty that the reusability of our button is limited because it's dependent on an implementation. But we know now that if we make use of the open-close principle, and we define an abstraction which can become the interface to our lamp, then when we remodel that abstraction back into our button, we have increased the reusability, because now we can take advantage of a variety of lamps. Unfortunately, if the next application that wants to make use of our button because it's also concerned with lamps, then unfortunately, the reusability of our button didn't really do us too much good. So it's not that reusable. The dependence inversion principle emphasizes who should be responsible for defining the abstraction. Now, in most cases, we're going to want to make use out of our concrete classes, our concrete objects. which is also known as low-level code. But in some cases, we're going to want to make use of our not-so-concrete objects or our high-level code. High-level code sometimes like frameworks. But unfortunately, we can't do so while our high-level code is currently tied to an application requirement as its dependency. So we need to get rid of that if we want to be able to make use of it again. So we're just going to dump that abstraction, but we know that applications require abstractions. They're the solid foundations to which we build our applications up and around, so we need an abstraction if we want this to be flexible. So what we're going to do is we're going to allow the client of our button, which is pushed, to define the abstraction to which it should be paired. Now, because I said that the client of the button is push, it represents the behaviors of the button. It could be pushed, it can be released, it can be active, it could be inactive, it could be on, it could be off, etc. And so the abstraction almost reveals itself. Now I call this abstraction iToggle, and the name itself is arbitrary, but the behaviors that it possesses merely reflect the internal state of the button. Now, when we refactor the abstraction back within our button, and our next application makes use of this button, then the only dependencies that it brings along are one that's particular to the button. And that's great, because that's exactly why our application wants to make use of our button. Now additionally, we've separated our button from any application dependencies. So in this case, our halogen lamp is no longer dependent, right? If it wants to make use of our button though, it must now adhere or conform to our iToggle abstraction, which was defined by the button. Now that's kind of ironic because it used to be the other way around. Our button used to be tied to an abstraction defined by our lamp, but now it's the other way around. We have inverted these dependencies. And the beautiful thing about it is because it's not tied to an application requirement, we can make use of additional application requirements. All they have to do is become subclasses by toggle and have now the implementations conform to an on or off to work with our button, and then they can just be supplied as arguments to our button to be able to work with them. All right. Having covered the solid design guidelines, as a developer you should feel a bit more confident, if not more comfortable, at understanding what it takes to write a bit more flexible code rather than rigid code. So this will provide us a context so we can continue moving forward with learning new object-oriented design. Design such as design patterns. Now they provide techniques used to solve additional problems, specific problems, but unfortunately they're a bit vague. And that's because they have to cater to a large audience. There's no possible way for them to be able to give you step-by-step instructions to solve a dilemma, as they have no possible understanding of your current scenario. So rather what they do is they provide you with a seed to which a solution will stem. And with your context and your abilities as a developer, you can cultivate this solution to meet the needs of your current application dilemmas. The strategy pattern. The intent of the strategy pattern is to define a family of algorithms and encapsulate each algorithm as its own individual object, which we'll refer to as strategy objects. Now, an intent of a design pattern represents the goal of a design pattern and informs the developer what he or she can expect to achieve or gain by making use of such a pattern. Now, in this case, we're going to create families of objects, or through inheritance is relationships of objects, so that we can interchange them at runtime. Now for this example, we're looking at an isolated aspect of a form. Particularly, we're regarding the zip code and its validation process. Now on the left, we have a drop-down menu which holds 3 countries: the United Kingdom, the United States, and Canada. Now upon a selection by a user, the algorithm, which will validate the zip code, will reflect the choice made by the user. You can see that behavior happening within our validate zip method. We're using 3 regular expressions as our algorithms, and each one pertains to a particular area or location. Now what we're going to do is we're going to apply our strategy pattern to these 3 regular expressions. We're going to turn them into a family of objects. We're going to encapsulate each one, and by doing so, well, it releases the need for our form to physically have to hard code these algorithms directly. The benefit is the decoupling of code which would otherwise bind it to a particular role, implementation, or application. Now currently, everything that's in this behavior relates to countries. But if our form was created flexibly, I know that this is just an isolated aspect, suppose it wants to make use of regions in the future. Well, it can't, because right now we're talking about countries. So by extracting these algorithms, it becomes more flexible. Additionally, right now these algorithms are fixed or hard-coded. And that means that they can't be reused, but by encapsulating them in their own objects, they can be used, they can be reused, and they can even be interchanged at runtime. Now, because we're going to encapsulate these as objects, we're making relationships. We know that we must devise them with the notion of the expectations of our clients' behaviors in mind. And so I call this abstraction I validate. Clearly, it's going to represent the behaviors of these strategy objects, but what is it actually doing? We're validating zip codes. Now, we could have just said validate to keep it broad, but then we could have opened ourselves to violating the list-off substitution principle. We're specifically trying to validate zip codes for this behavior. Now, you can see that our two subclasses become the subclasses, our strategy objects. On the left, we have the United Kingdom validation. On the right, we have our United States validation. They inherit that validate zip behavior to which they apply the appropriate regular expressions which are particular to that chosen country. Now we must refactor our form to work with our new validate abstractions. And we do so with another method called set validation strategy. Now, because we're not using fixed information anymore, we need to make use of a reference to hold on to the objects that we will create until the time that we need to use them. Now on the left, you can see we're holding all of our strategy objects. We have our United Kingdom validation strategy object, United States and Canada strategy objects. When a user now makes a selection, which in this case, they chose United Kingdom, we instantiate a United Kingdom validation to which we will supply our set validation strategy, which accepts a validate type, and it will just retain our currently passed object onto a reference called current validation. To which now, when the zip code is supplied and submitted, it will make use of the validate zip behavior possessed by our strategy object, which is retained currently on our reference, current validation reference. Now, if it wasn't United Kingdom that the user actually meant to select, but rather that of the United States, well, we instantiate a new object, a United States validation object, and we supply it to the behavior where it will now be retained and replace the previous strategy object, the United Kingdom validation object, and it will be retained by the current validation until it needs to be used to validate the zip code. We move on to the factory method. Now, the intent of the factory method is to provide an interface used for creating objects, but here's the caveat. It'll be the subclass to supply the appropriate object. In order to design flexible software, in order to design flexible software, we must isolate dependencies. That's been an ongoing theme. Now, we saw earlier with an example of a button, it was paired to a specific type of lamp, that the reusability was limited. But when we inverted those dependencies, the reusability of our button was enhanced dramatically. Now, any application requirement could simply become a subclass of iToggle and be supplied as an argument at author time, to which will then at runtime be paired with that of our button. But let's assume that our requirement for another application needs a specific type of button to be paired with a specific type of lamp, another halogen lamp paired with a specific type of button, a switch button. Well, we make the appropriate subclasses, and then we will instantiate the two as necessary. But for a moment, if you can recall back to the beginning of the presentation, the manager class that had to instantiate the three-persons class and how it became rigid forever, that's exactly what we're doing here. So some object, some context, may now possess two additional dependencies. Worse, if our application requires multiple buttons to be paired with multiple devices, and we exponentially increase these dependencies throughout our application. All right, this is scenario one. Consider scenario two. Sometimes a framework will be required maybe to work with an additional object. Perhaps it's related on or it's dependent to that object. But nevertheless, it's an example much like scrollable window. Now, scrollable window represents a framework that will become a some sort of scrolling object at runtime. And it'll be provided, whether it's going to be vertical or horizontal, at author time, to which at runtime it will instantiate the appropriate strategy object to help determine how to scroll the object appropriately. Now, while this may seem benign now, there will be an application requirement in the future that requires these two strategies to change. And if they change, then our scrollable window has to change because he's the one directly paired to their instantiation. Now, a framework should never have to instantiate objects, nor should it ever deal with objects explicitly or through its concrete class. We're going to make use of our factory method to help alleviate both these design concerns. And we're going to do so by ensuring that it's our subclass to supply the appropriate behavior. So let's begin with code that we've already become familiar with, our button class. And we know, because it's paired to a direct implementation of a concrete class, we know that's wrong for so many different reasons. We're not going to continue talking about it. We're just going to get rid of it and replace it with an abstraction. Our abstraction, iToggle. Now, by providing an abstraction in place of our explicit object, provides two benefits. The first, we isolated dependencies. And the second is we've invited extension within our framework. Now, if our application does require that we make use of the halogen lamp, then we will continue to do so, but it'll be our subclass who will instantiate the object for us. And we only want to know in our framework of that object through its inherited interface, which will be our iToggle. All right, now because I did say it's going to be the subclass to provide the object, we need to make sure that our framework can get this object on demand and as it requires. And to do so, we're going to employ the use of a method, which I call createToggle. Now, by calling or invoking this method will be the equivalent of instantiating the appropriate application requirement and returning it back to whoever is the caller. Now, because this method is concerned with the creation of an object and the supplying of an object, it is called a factory method. Now, you can always spot a factory method within code because the method name will always be prefixed by one of two words, create or make. Now, in this case, I chose create iToggle. But as I said, because calling this is dealing with instantiating objects, we are definitely not instantiating objects within this method, at least right here. And so I've defined this method as being abstract. And that's because if we were to define an object here, we'd be no better off a few slides back where we already were right here. We'd tie ourselves to implementations, and that's just not good. Instead, just as the interface of anything abstract, we expect that to be inherited to become the interface of our subclass to which it will implement. Now he represents, because you can see he's switch button, he represents the application requirements of the button that he was supposed to represent. So instantiating an object here is totally safe because we don't plan on making use of this object outside of this application requirement. He physically represents only an application requirement. Now you can see here is where he'll instantiate the halogen lamp, and he will return it back to the caller of this method. But we know that we want our framework to be the one who uses the product. We just want to know this product only through its interface, the iToggle. So the last step of the puzzle for the factory method is we're going to have to invoke that method, and we're going to do so right on top of our device reference. Now this way, at runtime, when we instantiate our switch button, it will bring along with it the underlying framework code, which at runtime will invoke the createToggler or factory method, to which is deferred to our subclass, who indeed instantiates the halogen lamp object and returns it back to the caller, which happens to be our reference. Now, when our button is pushed, the device goes on. We don't know what device beyond it's an iToggle. The device goes on. When we release, the device goes off. Now, because we're making use of extension within our framework, we can make a subclass that represents any variety of application requirements. So say our application requirement now requires a doorbell to be paired with the doorbell chimes. Well, again, we instantiate our doorbell class, and it will bring along with it the underlying framework. The createToggle will instantiate the doorbell chimes by calling that factory method, to which it will be returned back to our reference. Now when the button is pushed, we'll hear ding dong, and when it's released, nothing. I do want to revisit our strategy pattern for a moment. Now, it's possible to make use of multiple design patterns with other design patterns or compounded patterns. Now, earlier, we've been talking about isolating dependencies, but the instantiation of 3 strategy objects didn't really do any good for us to be able to release our form from knowing any particulars for that application. But now that we know of our factory method, we can instantiate those objects elsewhere and still supply them to our form at runtime and interchange them. Well, to do so, we will create a factory method on top of our reference, and we will supply it with a string of the chosen dropdown, or the country, where, because our subclass represents the application requirements, it can remain aware, knowing that we're going to make use of 3 countries, Canada, United States, and United Kingdom, so it can instantiate the appropriate objects to which it will return back to the caller, so that at runtime we'll be able to validate the button, and our form will remain unaware of what objects it was using. The abstract factory pattern. The intent of the abstract factory pattern is to provide an interface used for creating a family of dependent or related objects. Often we regard them as being parts of a collection. The caveat, though, is that we can't reveal the concrete classes of any of the products or where they come from. All right. Sometimes objects are related to one another or dependent on one another and therefore need to be used as a collection. Now all the collections within our application will make up a set. Now the company that I work for has a client who approached them and wanted to have a way or an application where businessmen can find SME channel partners within the United States. Now after the application was created, it was originally in the United States. But now since, they've expanded their market to 10 other areas. Now here are 2 of them. We have Mexico and we have the United States version side by side. Now immediately they may not look different, aside from the locations on the map, and that should be understandable. But the reality is they do possess subtle variations. Now there are some things that in America we make use of a zip code, and in Mexico they have no zip code. They rely on regions. So the client made it an application requirement to provide a drop-down menu. So we can provide the regions for them, and they can use that drop-down. They also didn't want some of the letters to be used for the identifiers. And now let me tell you, all 10 versions have their own subtle variations. But they're not that large that requires 10 separate applications, because they all make use of some of the same underlying behaviors and a lot of the same framework code. So instead of making 10 separate applications, we build up the other 9 on top of the original, but definitely not as conditional statements. That would bind us again to implementations and constant modification. We want to be open to extension, because they've already created 10, they might want to go for an 11th. And that means if we did it as an if-else statement, we'd have to track down all the different areas that we created these if-else statements. So, how did we handle this? Because every version requires its own assemblies, therefore it needed its own assets and has its own logic. But if you look at it from a bird's eye perspective, we can also pick out all the application requirements that were constantly varying. And then we created strategy objects for every single aspect. So we abstracted all the areas that were changing, and now all of our subclasses could represent the behaviors required by that particular location. So on the left, staying true to the Mexico and United States version, on the left of every single abstraction, we have the subclass that was necessary for our English version. And on the right, we have all the strategy objects that were necessary for the Mexico version. Now they don't do us very good just being scattered all over the place. While it may seem it might be easy to work with just the 4, there were plenty of areas that were abstracted, so this is just keeping it simple. So what we did was we localized, or we collected all of the strategy objects that were particular to a chosen area. Now here, you can see that our collection on the left is particular to the United States, and the one that's on the right is particular to that of Mexico. Now because we want to use all of the product together at the same time to display the final result to the audience from wherever they're coming from. Now we want to supply these back to our framework. Unfortunately, they have nothing in common that ties them together. So they need uniformity. And of course, to do that, we need to supply them an abstraction. And here you can see that we have our collection factory. Now all of our collections, all 10 of our collections, will become subclasses. But now because we're devising an is-a relationship, remember that we must devise our relationships with in mind of the output that our clients depend on. So our framework really doesn't just need our collections, he needs to be able to obtain the products within it. So our collection factory defines an interface used to do so. Here's all the abstractions that will be returned and the methods used. Hopefully you can guess that because it has create in the name, they are indeed factory methods. Now, these factory methods will be inherited as the interface to all of our subclasses. We have our United States collection currently, to which it implements all of the necessary details required to supply the products which are particular to the area that it requires back to the factory. Now we do the same thing with the Mexico collection. It inherits all of these interfaces, the factory methods to which it supplies the appropriate Mexico products. And we do the same thing for all 10 versions. Now the last step, as always, we refactor our framework back to working with our abstractions. Now up top, here's all of our product abstractions, and we pass in one of our collection factories. So at runtime, depending on where someone came from, we will supply it with any of the strategy objects on the left, the Germany factory, the France factory, the Brazil factory, etc., any of them. And now he will be able to obtain, our framework will be able to obtain the products that are contained within so it can build out the site as it properly needs. The thing is though, he will never be aware of the products he's using, and that's because they're all abstracted. Additionally, he will never know which collection they're coming from, because they too have been abstracted. So the only one who will ever be aware will be the audience, depending on which version they're looking at. Now, we don't really have any more time to go on to the MVC. That'll be available in my presentation notes when they come around and collect it. Two things, I would like to take some questions if any of you have. I also do have, if anyone here is an ActionScript developer and is still interested in learning about ActionScript as well as object-oriented programming and some more design patterns, I'd like for you guys to be able to walk away with those. There's only 10 of them though, so if you are an ActionScript developer, it's only going to really be pertinent to you in that material, but feel free to just come and grab one. Anybody have any questions or?
I did have one.
Sure. Is it possible to also raise the light so I can be able to see?
Free stuff, everyone run.
For JavaScript, it seems like there's a bunch of different ideas out there about how best to put some real object-oriented framework over top of it. Do you have any reference, like best practice for that, or some sort of?
The thing is, everyone's going to always have their own opinions on something. You got to also find what's going to work best for you. Now, I know that Grant, if you guys were at his presentation, he talked about 3 different ones, CoffeeScript. There were 2 others, Dart. They were all about trying to be object-oriented for JavaScript. One of my favorite ones, it's called Mascara Engine. Have you ever heard of it?
No.
Mascara Engine, it's written on Python. I don't know what type of editor you used, but it is also something that as long as you use Apache, you can install it on your own. Or if you have something that's built on Eclipse, then you can also just Mascara Engine. Now what's beautiful about it is you will physically type in object-oriented code. Strictly object-oriented code. All classes, everything is understood, and it will then compile it out to JavaScript. So I really do recommend that. That's the one that I enjoy myself. Anyone else? No? That's all right. I guess we have 8 more minutes if they wanted to take off, unless you have some questions or whatever. No, all set? What?
Keep going, Ben.
Oh, well, there's just not enough time, really. The MVC is one of where it's more of the most complicated because it is a compound pattern. It involves 3 different aspects, the model, the view, and the controller. But as I said, they will be available in the notes. And if any of you are really into object-oriented programming, you have any questions, I'm always available, so I don't mind if you want to take down my email address. It's iben@spilledmilk, spilled has a hyphen, spilled-milk.com. I have no problem fielding any questions. Early on in my career, I had many questions. And for the MVC, I actually went right to the source. His name is Tryg Vrienskog. He was the inventor of the MVC. And I was, I guess, ballsy enough to try and get in touch with him. And he was very knowledgeable, and I have no problem passing on any knowledge or trying to help out. That's pretty much what I enjoy doing. So yeah, feel free to give me a shout out if you guys have any questions or there's anything in particular that you're just stumbling on and you're wondering if there's a technique that you can use to be able to get out of that dilemma.
Question, abstraction, how does that relate to JavaScript? Like, as far as I know, there is not a lot.
No, but abstraction is something that you create yourself. So if you create an object, just don't supply it with a behavior, and that's going to become the founding object to which your objects are going to inherit from. So the thing about object-oriented programming is it's more of a conceptual thing.
Right.
As a developer, and that's why it is a bit of a difficulty, because you have to figure out the language, and that always helps the most. To be really good at object-oriented programming, you have to know the syntax of a language almost inside and out. So you know how to be able to make use of that object, the language. Right. And then you can apply the object-oriented programming to it. But by defining just an object, just leaving it there, you're never going to be using it, and you just inherit from that. Because it then gets the parent's type. Right. So much like an object, you can then supply it, and the object itself.
So that won't take a performance hit by having a bunch of those?
Object-oriented programming is always a performance hit, but that's not why these languages use it. It's because of the ability to be modular or have the ability, Okay. For speed, object-oriented programming is never going to get you. If you're going to do that, go for OpenGL or something that's totally inline. Yeah. But that's the problem with object-oriented programming. But all of the technologies like Android, all the phones, they're all making use of object-oriented programming strictly because it's flexible, it's modular. And we can be able to create code more easily and work in an environment of teams. But it does have its drawbacks, that's very true. And so that's why, especially in the books, I try and give you a lot of techniques that are limiting to ActionScript or how to be able to get more power out of certain uses of object-oriented programming.
And your notes, where would they be?
My notes for these?
I think that's what you said, yeah.
Yes. He's going to come around and collect them. I don't know when they're going to supply them.
They will be on the FITC website.
Thank you.
Okey-dokey. Super.
Great. Thank you very much, everybody.
Thank you.